Okay, so what could engineering light possibly have in common with teaching a machine to think? I mean, on the surface, you'd think absolutely nothing, right? One's physics, the other is AI. But it turns out two groundbreaking papers, published on the very same day, reveal this hidden blueprint for discovery that connects them both in a really profound way.
Our story really kicks off on one very specific day, July 28, 2006. On this single day, the journal Science published two articles that, in their own completely separate fields, would go on to set the stage for decades of innovation.
And that's the big question, isn't it? How could building new materials have anything to do with building new minds? You know, on one hand, you have the physical world, on the other, the digital. But the link between them? Well, it reveals a pretty incredible secret about how we can solve some of the most complex problems you can imagine.
So let's just lay out the two challenges side by side. On one side, you've got physicists trying to tame light itself, to literally create materials that can bend and twist it in ways that nature just can't. And on the other side, you have computer scientists trying to tame complexity, teaching a machine how to find that one simple truth hidden inside a total storm of chaotic data. All right, let's tackle the light first. We're about to enter the strange and frankly super cool world of metamaterials.
So what in the world is a metamaterial? Well, think of it this way. It's a substance where the magic isn't about what it's made of, but how it's built. Its amazing properties come from its tiny engineered structure, not from its chemistry. It's all about the design.
Honestly, the easiest way to get your head around this is to picture it like building with Legos, but instead of for a castle, you're building for light waves. By arranging these tiny, simple structures in a super precise pattern, you can create a bigger block that has these entirely new, almost magical abilities.
So what did the scientists actually do? Well, they created billions of these microscopic U-shaped metal rings. Then they just zapped them with a laser. What they were looking for was this really rare effect called second harmonic generation. A good way to think about it is like a guitar string. You pluck one note and you hear this perfect higher octave note sing back. They wanted to see if their little structures would sing back at double the light frequency they put in.
And the result? Whoa. It was just staggering. The signal they measured was 500 times stronger than any of the background noise. I mean, this wasn't some tiny, subtle little effect. This was a loud, powerful, undeniable response.
And that was the proof they needed. See, before this, we were pretty much stuck with materials that could only bend or block light. But this experiment showed we could actually build structures that fundamentally transform it, creating powerful new behaviors whenever we want. A whole new toolkit for physics was basically born that day, opening the door to wild ideas like super lenses and even invisibility cloaks.
Okay, so let's hit pause on that idea for a second. We're going to leave the physics lab and jump right into the world of data, because it turns out an equally massive problem was being cracked on that very same day.
The challenge here is this thing called dimensionality reduction, which sounds complicated, but the idea is simple. Take an image of a handwritten number. It's made of hundreds of pixels, right? That's a ton of data. But the actual idea of the number 2 is incredibly simple. So how do you teach a machine to find that simple code, that 2-ness that's buried under all those pixels?
The tool for this job is called an autoencoder. It's a really clever type of neural network. The way it works is you feed it an image, and you force it to squeeze, to literally compress all that information down into a really short, simple code. And then it has to try and recreate the original image perfectly using only that tiny bit of code.
So it really works in 2 steps. You've got the encoder, and its whole job is to do the squishing part, compressing the image into that efficient code. Then you have the decoder, which has to take that code and try to rebuild the original image. And here's the kicker. If the final image looks good, it means the network has successfully figured out the absolute most essential patterns in the data.
But, and this is a huge but, there was this massive problem. For decades, computer scientists knew this idea should work. But every time they tried to make the networks deep, with lots of layers to learn really complex stuff, the whole training process would just completely fall apart. It was a huge roadblock for the entire field of AI.
And this is where Geoffrey Hinton and his team entered the story. They came in with this incredibly elegant breakthrough, a totally new way to teach these deep networks how to learn.
Their genius idea was to stop trying to train the whole massive network all at once. Instead, they did it layer by layer. First, they just taught layer 1 to find simple patterns in the data. Then they took those patterns, fed them to layer 2, and taught it to find patterns in the patterns. And they just kept going. Once all the layers were stacked, they'd do a final fine-tuning to get it just right.
And it worked. Oh my gosh, did it work? This wasn't just a small improvement. This was the key that finally unlocked deep learning and kicked off the entire AI revolution that we're all living through today.
I mean, just look at the difference here. You don't have to be a computer scientist to see it. On the left, that blurry mess is the best that the old methods could do. But on the right, wow, the new autoencoder reconstructs the number with incredible clarity. The error numbers really tell the story. The new method was more than 4 times more accurate. It's not even close.
And this quote from the paper itself just perfectly captures the moment. Hinton's basically saying, look, we've all known for decades that this was the answer. We just couldn't figure out how to get it started. Well, his team had finally found the key.
So now we've got our 2 stories. A huge breakthrough in physics, a huge breakthrough in AI, and they were published on the exact same day. So let's finally connect the dots and see this shared blueprint.
So what's the big connection? What's the secret? It's that both of these teams stared into a storm of overwhelming complexity, and they found a simple, elegant structure hiding inside.
And this right here is the shared blueprint. Think about it. Both of them started with something overwhelmingly complex. Messy light waves on one side, messy pixel data on the other. Both built a layered model to find the signal in all that noise, stacked rings of metal versus stacked layers of neurons, and both used that structure to boil all that chaos down to a simple, powerful truth. And this is the part that I think is just so beautiful. It's the exact same fundamental idea, just expressed into totally different languages. One team built their layers from metal to decode the physics of light. The other built their layers from math to decode the patterns in data. And that really leaves us with this final, fascinating question. This layered approach to taming complexity has proven to be so incredibly powerful. It just makes you wonder, in science, in art, even in our own lives, what other complex worlds are out there just waiting for us to find the right way to stack the layers and reveal the simple, elegant truth that's hiding inside?